Swayam Prabha. Digital India. Educated India.
In this lecture, we shall discuss basics of relations. So, what is a relation? Informally, it specifies which entities are related to which other entities. A little more formally, you could think of a relation as a predicate over the domain S cross S. That's a cross product, Cartesian product of S with itself. So the elements of S cross S are pairs. So in this example, S is the set consisting of Alice, Jabberwock, and Flamingo, and S cross S consists of these 9 elements. And a predicate in this example likes, assigns true to those pairs for which the relation is said to hold. So that's what a relation is. Equivalently, you could think of the relation in terms of the subset of S cross S for which the predicate is true, so that the predicate is the membership predicate for this subset. So in this case, there are 4 pairs for which the predicate is true, so the relation consists of these 4 pairs. Just a quick note, you could define something much more general. You don't need both sets here to be the same. That would be called a heterogeneous relation. We shall mostly focus on homogeneous relations. And further, you could have something which is more than binary. So you could, for instance, have a ternary relation. So instead of relations consisting of pairs, you can have triples, for instance. That would be a ternary relation. Okay, but in this lecture, and unless otherwise specified, we shall talk about binary relations, binary homogeneous relations. Okay, and one note on the notation. So for predicates, we have been using notation in this form. Some name of the predicate used as a function that takes entities as arguments. For relations, we would typically use some symbol. For instance, here greater than or equal to, and you would say x greater than or equal to, instead of saying some predicate called greater applied to x comma y. We would use the notation x greater than or equal to y to say that the predicate holds for x and y. Other symbols are also used, square less than symbol, or this tilde. Sometimes you just write a letter instead of a symbol, and sometimes you would write it out in English, so that you can read it as x likes y. There are several ways to look at a relation, and they're all useful ways to think about them. So the first one here is as a set of ordered pairs. That's exactly what we just now described it as. So if your relation is denoted by the symbol A is related to B, the set that stands for the relation is a set of ordered pairs A comma B. So the order is important. So in this case, the example would be, there are these 4 pairs in the set. Another way to look at this relation is as a Boolean matrix. So this matrix is 3 by 3 because I have 3 elements in my domain. It could be an infinite dimensional matrix too. Mostly we'll use finite dimensional sets as for illustration, but this could be infinite dimensional too. And each cell in this matrix corresponds to a pair of the form, a pair in S cross S. So so F comma A, F for Flamingo and A for Alice, is represented by the cell here. The row indexed by F and the column indexed by A, that corresponds to the pair F comma A in S cross S. And the entries in this matrix denote whether the relation holds for that pair or not, whether that pair belongs to the relation or not. So there are 4 true entries here corresponding to the 4 elements in the subset. So A comma A, J comma J, F comma F, and A comma F. Right. So those are the 4 entries that are highlighted or lit up to indicate they are true. And the final useful way to look at a relation is as a directed graph. Now, graphs is something we'll come back to and discuss in much more detail later. For now, all you need to know is that a graph consists of what are called nodes. So these circles here, A, J, F, labeled with A, J, F, they stand for the entries in S. So there's a node, these are the nodes. So each element in set S has a node in the graph. And we put this arrow or an edge for every pair. So if there's a pair A comma F in the relation, so you put an edge directed from A to F. So the arrow points towards F. And also you might have pairs like A comma A, they are represented by arrows that point to the nodes themselves. So that's called a self loop. Okay? So that's a directed graph. The edges are these directed arrows, and for every pair here there will be an edge. It could be in particular a self loop, or it could just be an edge from one node to another. You could also have, for instance, if Flamingo likes Alice, if the relation was to be modified so that F comma A is also in the set, then you would have had another arrow here, and there will be both these arrows in the graph. Okay, so that's a graph representation of a relation. And as we shall see, all these 3 ways of looking at it would make it easier for you to visualize various properties of relations. Okay. All right. So let's now get into some ways of using relations. And first I want to tell you about operations you can do on relations. And just like since relations are sets, they are subsets of S cross S, all the set operations are, can be meaningfully translated to operations on relations. So in particular, you could talk about there's a unary operation, namely complement, which takes a relation and gives you another relation in which all the pairs in the complement relation are exactly those which are missing from the original relation. And here, complement is with respect to a universal set. The universal set is S cross S. Okay, so that's a unary operation. You could also talk about binary operations, so union, intersection, symmetric difference. All the set operations translate to operations on relations. And again, all the properties we had, like associated it. So you could have union of multiple relations, not just 2 relations, and that's a well-defined operation on relations. Now, there are some other operations which are not just set operations, or rather they rely on the extra structure in a relation that it is a subset of S cross S. So this operation called converse or transpose takes a relation R and gives you a new relation R transpose, which consists of pairs XY such that the pair YX in the opposite order is in the relation R. Okay. Here again, XY need not be distinct. Some pair XX is in R, it will be in R transpose also. But otherwise it's swapping the order of elements of the pair. So it has essentially the same information as what R has, as just that the order is reversed. For instance, if you have a relation likes that we saw, you could define a transpose of it, which you could call is liked by. So X is liked by Y if and only if Y likes X. In terms of the graph representation, if the original relation R, had an edge like this, so the yellow edge, then in the transpose there will be an edge going in the reverse direction. And in terms of the metrics, the transpose relation is actually a transpose. It corresponds to matrix transpose. So X is related to Y in R transpose means the xth row and yth column, the cell in the xth row and the yth column. That is true if and only if in the original relation the cell in the yth column and yth row and xth column was true. Okay, when I say xth row, I mean the row indexed by the element x, and similarly for column. Okay, so here the matrix that corresponds to the representation of R transpose is the transpose of the matrix that corresponds to the relation R. Another useful operation between relations is composition. So denoted by, so this you can read as R composed with R prime. R and R prime are two relations. So R composed with R prime has a pair XY if and only if there is some element in S such that some element W in the set S such that XW is in R and WY is in R prime. So in terms of the graph, it looks like, so X and Y, if it is the case that there is some other, or some possibly one of them, some node W, or some element W in S, such that the yellow edge here represents the relation R. So such that X and W are related according to R, and W and Y are related according to R prime. The blue edge corresponds to R prime. And if that is the case, then X and Y are related according to the composed relation. Okay, that's the definition of the composed relation. In terms of matrix representation, so in the composed relation, X is related to Y. If there exists some W such that M of XW is true and M prime of WY is true. So here M and M prime are the matrices corresponding to R and R prime. So the XY cell in the matrix correspond to M composed with, or of R composed with R prime is true if and only if for some W this turns out to be true. In other words, the disjunction, right, the OR over all possible values of W of MXW and M prime WY is true. So this you could view as a matrix multiplication, except instead of multiplication you are doing and instead of addition you are doing OR. So this is called a Boolean matrix multiplication. Composition corresponds to Boolean matrix multiplication in the matrix representation. All right, so those are the relations I wanted to mention. Now let me talk about a few different kinds of relation or types of relation. The first one is what's called a reflexive relation. Okay? And it simply says that it's a kind of relationship that you have with yourself. Okay? For instance, X knows X, or in terms of integers, let's say X is less than or equal to X for any X. So the relation always holds, for pairs of the form X comma X. So all pairs of the form X comma X are contained in the relation. So in terms of the matrix representation, it looks like the diagonal here is all lit up, because those are the entries of the form, the row and column. So here the third row and the third column that cell, whatever the third element is in S, that cell is in, that pair is in the relation. So that corresponds to the diagonal entries being all turned on or turned true. In terms of the graph representation, it says that all the um, nodes have self loops. Okay, so every node has a self loop on it. That's what a reflexive relation is. Again, these representations make sense for finite sets S, but the definition of reflexivity extends to infinite sets also. It just says that for every x in S, x comma x is contained in S. Okay, yeah, so this is, in terms of the visualization, this is what a reflexive relation looks like. There is a notion of an irreflexive relation, which is kind of the other extreme of this, which says nobody should be related to themselves. So as an example, say give birth to, assuming that you cannot give birth to yourself, that would be an irreflexive relation, or not equal to would be an irreflexive relation. Okay, and that corresponds to all the diagonal being switched off and there being no self loops. Okay. Now these are kind of two extremes. You can have relations which fall in the middle, where there are some, also there are some self loops but not all self loops, right? So that, as an example, is a prime factor of. So sometimes if you're a prime number, you would be a prime factor of yourself, but otherwise, if you're not a prime number, then you're not a prime factor of yourself, right? So some have it, and with this is a relation some elements have with themselves and others do not. Another interesting kind of relations are what are called symmetric relations. So a symmetric relation is a relation that is reciprocated. That is to say, if x is related to y, then y is related to x. As an example, say you're in a classroom, then I could talk about, a student x sits next to student y as a relation between x and y. So if x is sitting next to y, then y is sitting next to x, right? So that would be a symmetric relation. In terms of the metrics, it says that it's a symmetric matrix. Okay, so that's the name for symmetric matrix. Also, that's the reason for the name. If the ijth entry here or the xyth entry here is turned on, then so would be the yxth entry. And vice versa. If it's this is turned off, then this would be turned off. Okay, and in terms of the graph representation, this means that every edge is accompanied by its reverse edge. So the edges appear as bidirectional edges. They come in as a pair. Of course, this says nothing about what should be the case for self loops. Some self loops may exist, and some self loops may not exist. So in the diagonal here, it could be either lit up or not lit up. What symmetry says is about pairs of the form x, distinct x and y, right? Pairs of the form x comma y with distinct x and y. If there is such a pair, then y comma x is also in the relation. Okay. Yeah. So if a graph for a symmetric relation consists only of self loops and bidirectional edges, note that I'm not saying all such self loops will be there or all possible bidirectional edges are there. There are missing edges here, but whenever there is an edge, it's either a self loop or it's a bidirectional edge. It's accompanied by its reverse edge. Again, there is another extreme of this, which is antisymmetric, which says that there is no reciprocation except possibly with self. So again, parent of would be antisymmetric. If say your mother is your parent, then you are not your mother's parent, right? So that's an antisymmetric relation. A prime factor of, again, is another example of an antisymmetric relation. If x, so again, it's some elements may be their own prime factors, or some may not be their own prime factors. But if x and y are distinct, then if x is a prime factor of y, then y cannot be a prime factor of x. So remember, a prime factor is a positive factor, and it's a prime number. So if x is a prime factor of y, and if x is not equal to y, then x is actually a number which is either y is negative, or so therefore y cannot be a prime factor of x, or x is a number which is strictly smaller in magnitude than y. Okay. Another example similar to parent of is, well, here is a subset, or it could be an equal subset, right? It's not a strict subset. So the subset of relation again is anti-symmetric, and in this case it is reflexive as well. Okay. In terms of the graph, what it means is that there are no bidirectional edges. It doesn't say anything about whether self-loops exist or not, but there are no bidirectional edges. And here you can have relations which are outside of the spectrum of being symmetric or anti-symmetric. If you took a relation like likes, some pairs, in some pairs the relation is reciprocated, and in some other pairs it's not reciprocated, right? X likes y, but y doesn't like x. So this is an example. This, in our Alice, Jabberwock, Flamingo. Well, or if you also had entries there where things were reciprocated, then it would have been it would have neither been symmetric nor antisymmetric. Our particular example happened to be antisymmetric because the Alice liked Flamingo, but Flamingo didn't like Alice, and the only other relations were with themselves. Okay. You could also have, yeah, so in terms of edges, it means there are some edges which occur with their flipped direction, but then there are other edges which occur by themselves without their reversed edge. You can also have relations which are both symmetric and anti-symmetric, and that would be the case of a relation which is in which all the entries are, all the pairs are only self-loops. They're only pairs in the diagonal, right? So if you want to satisfy both these requirements, it says the only edges are self-loops or bidirectional edges, but hey, you cannot have any bidirectional edges, so all you can have are self-loops. So that's what a symmetric and anti-symmetric relation would look like. Again, not all self-loops need to be present, but whatever edges are present need to be self-loops. The third kind of relations want to discuss are transitive relations. And some examples of this are, so we had parent of as an anti-symmetric relation, but here my example is an ancestor of. Okay, so it need not be your parent; it could be your parent's parent or their parent, and so forth. So that's an ancestor of, or subset of. That's an example we already had. That happens to be a transitive relation. So what is a transitive relation? So here it says that if A is related to B, right? So if A is a subset of B, for example, and B is related to C, and B is a subset of C, then A is related to C, then A is a subset of C. Right? So A is contained in B and B is contained in C, then A is contained in C. So that's why subset of is an example of a transitive relation. So this is a definition of what it means to be a transitive relation. So if whenever there is a pair A comma B and a pair B comma C, the pair A comma C should exist. Okay, that's a requirement on a transitive relation. Another way to say that is if you consider R composed with itself, right? So if A is related to B and B is related to C, in R composed with R, the pair A comma C will be there. And in fact, that those are exactly the pairs in R composed with R. And the transitivity definition is just saying that all such pairs, the pairs that occur in R composed with itself, they should already be in R. Okay. So R being transitive is the same as saying R composed with itself. It's a subset of R. Is contained in R. So let's try an example here. So here is a relation I'm building. So I have a bunch of nodes. I have a few edges here. Is this transitive already? So here, I have, say, think of this A is related to B and B is related to C, but I'm missing this relation between A and C, right? So I could try adding that, but there are more. Say, think of this as A now. A is related to B and B is related to C. I was missing this edge too, so I could add that also. So I added these edges which were missing. But in the process, I have created a new pair. Now think of this as A and this is B. So A is related to B. This is a new edge I just now added. And B is related to C, but I'm missing the edge between A and C here. So I could go ahead and add that as well. And at this point, if you check, this condition is going to hold. Whenever there is, there are these kind of two edges here, there will be an edge completing the triangle. Another way to look at this is to say, look, in the original, what I gave when I started off with a few edges missing, you could already see a path from this node all the way to this node. So path is just a sequence of arrows that you follow. And we will be more formal about a path when we talk about graphs. But for now, it's just, this informally you can see what a path looks like. It's just following these arrows. So there is a path that could take you from this node all the way to this node. And we saw that to be transitive, this edge had to exist because, this edge had to exist. And then we argued, okay, if this edge exists, then this edge also has to exist. So whenever there's a path, you can argue that, so when there is a path from A to Z, you can argue that there has to be a direct edge from A to Z. Okay, so that is what transitivity implies. Okay, or in other words, in terms of the composition, so this I could call R square, right? R composed with R, so 2 times R occurring there. I would call it R square. More generally, I can talk about R to the power K, which just means R composed with itself, and there are total K R's there. And what R to the power K consists of are all the pairs that are connected by paths of length K. And what we are just not saying is that to be a transitive relation, this R to the power K has to be contained in R. And that's actually easy to see. If you take this as a definition of transitivity, then clearly, for k equal to 2, this is already stating this, so the implication in this direction is clear. In the other direction, you can prove by induction, because R composed with R, so if you take, for instance, R composed with R composed with up to k times, that's basically R composed with R and so forth, k minus 1 times composed with R. But the first k minus 1 composition, R to the power k minus 1, inductively is a subset of R, and the base case being k equal to 2, and then it implies that so if, some subset of R composed with R is a subset of R composed with R. So R to the k is equal to R to the k minus 1 composed with R, which is a subset of R composed with R, which is R. Okay, so it's the whole thing is a subset of R. Here, again, you could define another extreme of transitivity called, which you could call anti-transitivity. We'll skip that kind of a definition. However, we will use the term intransitive sometimes just to mean not transitive. Okay, so this condition does not hold, then we call it not transitive or intransitive. All right, so just to summarize the types of relations, we talked about reflexive and irreflexive in terms of the self loops, all of them being present or all of them being absent. We talked about symmetric and antisymmetric in terms of all the non-self loop edges being, all being bidirectional or all being unidirectional. And we also talked about transitive relations, namely, if there is a path, then there is an edge. If there's a path from A to B, then there should be a direct edge from A to B. Now, these three properties, reflexive, symmetric, and transitive, so they are satisfied by adding more and more edges. For instance, in particular, the complete relation, which is just S cross S, satisfies all these properties, right? So if you found something, so when we took the previous example, we found a relation which is not transitive, I could just keep adding more and more edges until it became transitive. In the worst case, I might end up adding all the edges, but at least then I'm guaranteed that at that point it will be transitive. Similarly, if I have all the edges there, then then all the non-self loop edges are bidirectional, and it will be symmetric. And similarly, if I have all self loops, so if I have all edges, I have all self loops, and then it will be reflexive. Okay, so these three properties are, in some sense, properties I can achieve by adding more edges. I might also lose this property by adding some edge, but then I can keep adding more edges and get back this property. Okay. Now, so you define these closures. So reflexive closure, well, that's actually very simple. So reflexive closure just means that you're given a relation R, you define some relation which contains it, a superset of R, which is reflexive. Okay. And of course, you could have taken the complete relation itself, that is a superset of R and is reflexive. But we are interested in the minimal such relation. So here minimal means if I remove even one pair from this relation, it stops satisfying one of these properties. Either it stops being a superset of R or it stops being reflexive. Okay, so reflexive closure is such a minimal relation. And in the case of reflexive closure, it's pretty simple. What you need to do to get a reflexive closure, you have to take all the pairs in R. You also have to take all the self loops. So you just put all of that together, and what you have is a reflexive relation that contains R. And it couldn't have been any smaller than this. So this is the minimal relation containing R. So that is the reflexive closure of R. Similarly, symmetric closure is defined as a minimal relation containing R, which is symmetric. And here again, it's pretty straightforward what you need to do. You need to take all the edges in R, and if you ever find an edge which is not a self loop, and if it is unidirectional, you make it bidirectional. You put in the edge in the reverse direction also. And you don't add any other edges. You don't add any other self loops. You don't add any other edges other than, making for what you need to do to make unidirectional edges bidirectional. And again, the edges you added are all necessarily there, have to be there in any relation R prime containing R, which is symmetric, right? So, and what you end up with after you, put make all these unidirectional edges bidirectional, what you get is a symmetric relation. So that is a symmetric closure of R. Transitive closure may be a little less direct to see from the original definition we had, which is saying if A is related to B and B is related to C, then A is related to C. But if you think in terms of the way it's presented here, that if there is a path from A to B, then you have to have a direct edge from A to B, then it's clear what transitive closure of R should be. You start with all the edges in R, then you find out all pairs AB such that there is a path from A to B in the relation R, and just put in all those new edges. They all need to be there in transitive closure of R. And what you end up with is now transitive, because in this process, when you added these edges, you never created any new path, as in you never created, if there were two nodes A and B, which originally did not have a path between them, by adding an edge, adding your new edges, you didn't create a path. The new edges you created all corresponded to paths that already existed. So even if that edge was not present, you could have gone from A to B by taking some path. So you can make this more formal using an inductive argument, and we'll do these kind of arguments when we talk about graphs. But for now, we can just intuitively convince yourself that this is a transitive closure. Okay, so I define, for the purpose of definition, to be well defined, I defined everything as minimal relations. Then I know it's well defined because there is some relation, and then there are these minimal relations which from the well ordering principle I could obtain if I had some numbering, for instance. However, it's better than that. It's not just that there is some minimal relation. There are exactly these particular minimum relations in some sense that I just now went over. So there is a unique reflexive closure, there's a unique symmetric closure, there's a unique transitive closure of a given relation R, each of which is obtained by adding some set of edges that are necessary to make it satisfy the corresponding property. Okay. All right. So you should think about that. That these closures are well defined and that they are unique. And the example we saw with that in the previous slide about making a graph, making a relation transitive by adding more and more edges corresponded to constructing the transitive closure of a given relation. All right, so the last kind of relation I want to cover today is a combination of these three interesting properties that we just now defined: reflexivity, symmetry, and transitivity. Okay, so it's called an equivalence relation if it is reflexive, symmetric, and transitive. Okay, and some examples are so is a relative. So if I'm you're say if you are my relative and you have an uncle, so your uncle is a relative of yours, then I'm a relative of your uncle as well, right? If I'm a relative of you and you are a relative of your uncle, then I'm a relative of your uncle, so that's transitivity. I'm a relative of myself, that's reflexivity. And if I'm your relative, then you are my relative, that's symmetry. Okay, so being a relative is a real life example of an equivalence relation. Um, maybe everyone in this world is related to everyone else, but it's clearly an equivalence relation. Another example, more familiar example, I guess, for us would be to say two, say, positive integers, they are related to each other if they have the same last digit in decimal. Okay? So, 33 and 103 are related to each other. 33 is related to itself. If 33 is related to 103 and 103 is related to 23, then 33 and 23 are related because they have the same last digit, right? 3. It's also symmetric. 33 is related to 103, 103 is related to 33. So that's another example of an equivalence relation. So that actually is congruence with respect to 10, but more generally, congruent modulo with respect to any modulus is transitive. Sorry, is an equivalence relation. Okay, it is transitive. It's also reflexive and symmetric. So it's an equivalence relation. Now, when we were talking about congruence, we defined a congruence class, right? So we would take a number and say, okay, let's look at all other numbers that are congruent to it, and that would be the congruence class of that number. So similarly here, more abstractly, you can define an equivalence class. So given a relation, which I am denoting by this similar symbol, or you could think of it as a tilde. So if x is, so the equivalence class of x is a set of all y's such that x is related to y according to this relation. Okay? So the equivalence class corresponding to this relation is defined in this way. Okay, so it's all the y's that x is related to. Okay, so we say the relatives of x. Okay, so that's the equivalence class of x. Now, first thing I want to point out is that every element is in some equivalence class. Every element is somebody's relative in the example of relative. Why? Well, in particular, we know it's its own, because of reflexivity, we know it's related to itself, so it's in its own equivalence class. It may be related to others also. I mean, there may be, other numbers, other elements to which it is a relative, but it's related to itself. So at least we know that it's in some equivalence class of some x, namely itself. Okay. And secondly, if say x and y were two elements such that their equivalence classes intersected, well, then that can happen only if their equivalence classes coincide. Their equivalence classes have to be exactly the same. If they share even one common element, then they have to become the same. They have to be the same. Okay. So let me prove this. Actually, pretty simple. So what is it? What do I want to prove? Suppose this there are some x and y such that their equivalence classes have a non-empty intersection. Okay, so pick any such xy, and since they have a non-empty intersection, I can pick some element in it. So let me say that element is z. Okay, so z is in the equivalence class of x and z is in the equivalence class of y, meaning z is related to x and z is related to y. That's why z is in the respective equivalence classes. What I would like to show is that, just using this much information, I want to argue that equivalence classes of x and y are equal. Okay, which means I could show that equivalence class of x is contained in equivalence class of y and vice versa. And since things are symmetric, I'm just going to show that equivalence clause of X is contained in equivalence clause of Y. The other argument follows symmetrically, right, by interchanging X and Y. Okay, so what I need to now show is that equivalence clause of X is contained in the equivalence clause of Y. So let's pick an arbitrary element in the equivalence clause of X, and we'll show that it's an element in equivalence clause of Y, right? So let's pick an arbitrary element in equivalence clause of X. It could be X, Y, Z, it could be any of these two, but just for clarity, I've drawn it as a separate element here, a separate node W. And all we know is that W is in the equivalence clause of X, so there is an edge from X to W. This could be a self-loop if W is the same as X, but there is an edge from X to W. Now, that by itself, I've used, yeah, so that by itself is like not very useful right now. If you look at this picture, I certainly don't seem to be in a position to use transitivity. I could use reflexivity to say they're all self-loops, but the useful step here would be to notice that I can appeal to symmetry and add the reverse edges. In particular, by symmetry, I can say there has to be an edge from Z to X. Z should be related to X. Okay, so once I put this edge, then suddenly I see I can talk about there being several new edges by looking at transitivity. In particular, you can take this path from Z to W, which earlier you couldn't, right? Because the X to Z edge was in the reverse direction, and path has to follow the direction of the arrow. But now that I know there's an edge from Z to X, I know there's a path I can take from Z to W, and transitivity says in that case there should be a direct edge from Z to W. Now that I have directed from Z to W, well, even otherwise, right, I could have seen that there is a path from Y all the way to W. I just broke it up into two steps, saying, okay, there is a direct edge from Z to W, and that immediately lets me use transitivity in terms of its definition and say conclude that there has to be an edge from Y to W. Okay, so in both these cases I use transitivity just to kind of complete the triangle as it was defined. And now what do I have? I have an edge from Y to W. And that's exactly what it means to say W is in the equivalence clause of Y. Okay, and that's what I was setting out to prove. Any arbitrary W in equivalence clause of X is contained in, is an element of Y also. So every element in equivalence clause of X is an element in equivalence clause of Y, okay, which is what I set out to prove. All right, so that is a quick, simple argument to show that, to prove this claim that if equivalence clauses overlap, then they have to coincide. And these two things together tell you that equivalence clauses form a partition of the domain S. Okay, so what is a partition? So a partition is a bunch of subsets of S. So here I'm calling P1 to Pt. So distinct subsets of S, such that together they cover the entire S. So their union is all of S, namely every element in S belongs to at least one of these elements, one of these sets, P1 to Pt. On the other hand, these sets are all pairwise disjoint. They, P1 and P2, for instance, are disjoint. They have zero intersection. Okay, they have an empty intersection. If so, here what it says here is that if they have an intersection, they have a non-empty intersection, they are the same set. Then I would have called them both, say P1, right? So if you have T distinct sets here, every pair of them, so this is what a partition is, the T distinct sets such that every pair of sets are disjoint from each other. and together they cover the entire set S. And these equivalence clauses satisfy that because this point here says that every element in S lies in some equivalence clause, and this point here says that um, these equivalence clauses, either they are, if you take two equivalence clauses, either they are the same, so I'd give them the same name, or they are disjoint from each other, right? So pi intersect pi is of course pi, but pi intersect pj where I not equal to j is empty. So here that's what I mean by pi intersect pj equal to empty. For distinct pi and pj, they are disjoint. Okay, so these equivalence clauses form a partition of the set S, and this is what it means to be a partition. So it's actually simplifies a picture of an equivalence relation a lot. So all that means is that say for relative, basically it says the world would be separated into disjoint families. Within each family, everybody is related to each other, and then across families, nobody is related to anyone else in another family, because if they were, then they would become the same family, right? So the world is partitioned into families, and across families, people are not related to each other. Or in terms of the metrics here, so by the way, hopefully, maybe the whole world is a single family. That's also possible, right? Everybody is related to everyone else. That would be an equivalence relation as well. Here, so this is what a matrix representation of the equivalence relation would look like. Once you sort the sets, once you sort the elements here, so you pick one equivalence clause, write down all the elements in that equivalence clause, you get a block. In this case, there was only one element in that equivalence clause. Then you took another equivalence clause which had three elements, and they're all related to each other, so you get a square block here. And you don't, so along the diagonal you have these squares corresponding to equivalence clauses. It's all lit up because everyone within the equivalence clause is related to everyone else, right? So the equivalence clause of x, say take an element here x, equivalence clause of x is this entire set. So everyone here is lit up. On the other hand, there are no other lit up cells outside of these blocks, because that would have made, say, if there were to be a position here that is lit up, then the equivalence clause of x couldn't have just been this much. It would have had to have that element as well. Okay, so since the equivalence clause is partitioned, the domain, you cannot have one of those elements, its equivalence clause, having an element from another equivalence clause, okay? Unless they are the same equivalence clause. Right, so that's what it looks like if you were to visualize equivalence clauses. In terms of graphs, you could visualize them as these cliques, right? So these would be our families. Within the family, everyone is related to everyone else, so these are called cliques. So within the clique, everyone is connected to everyone else, but across cliques, there are no connections. Okay. All right. So just to put that equivalence relation into our gallery here. So this is all the it's basically a relation that is reflexive, symmetric, and transitive. And it's its own an equivalence relation, since it's already reflexive. It's its own reflexive closure. It's its own symmetric closure. It's its own transitive closure. And you could talk about an equivalence closure, and an equivalence relation is its own equivalence closure. All right, so that's all for now, and we'll continue with more types of relations in the next lecture.